Hi. I want to talk about a really cool method for doing some integrals, which is the method of substitution. Some people call it U substitution. I'm just going to call it substitution. And what the method does is it undoes the chain rule. So let me remind you what the chain rule is. Okay, so the chain rule says that dx of f of g of x is equal to f prime of g of x. And then I have to chain out the derivative of the argument times g prime of x. So the things that we are going to attempt to integrate using the method of substitution are those of the form like this. I guess I should probably write down a few examples of things. So for example, we could try integrating the function sine to the 9th of x times cosine of x dx. So this is so this function right here is the derivative of, that's the derivative of sine to the 10th of x, right? Because I have well, up to a scale, right? So up to a scale. So we'll deal with scalars when we deal with a particular point. So don't worry about the scaling factor in front, the coefficient. We're just worried about right now, just thinking about the actual form of the function. So I've got something to the 10. So when I take the derivative of this, I'd get my 10 is somewhere else. And then I'd have that thing to the 9th power times the derivative of the inside. And the derivative of sine is cosine. So this function right here that we're going to integrate, this integrand, is the derivative of a composition of functions, which is what makes this a great candidate for the method of substitution. Let's do a quick another example, not the method of substitution, but just trying to get you to get a feel for the types of problems, the types of integrands that work well for this. So I might have the integral of 2x plus 1 over x squared plus x plus 5 dx. So the thing that we're kind of hunting for when we're doing substitution is we're looking for something that's the derivative of something else. In this problem, it was cosine was the derivative of sine, and the more complicated, like the bigger function was to the 9th. And then this thing is like just the derivative of the thing that's to the 9th. So this one right here is like something over something. And look at the top. I've got 2x plus 1. And in the bottom, I've got x squared plus x plus 5. And the derivative of the bottom right here, the derivative of this is the top 2x plus 1, right? So the top here is the derivative of the bottom, which means that there's some sort of composition going on as far as this goes. So there's a strong hint when we see the derivative of another part of the integrand, and that's going to hint that we're going to be doing the method of substitution on it. Namely, this right here, this integrand right here, is the derivative of the natural log of x squared plus x plus 5. Okay? Because the derivative of a natural log is 1 over. And then if we were to chain out that, then we'd have the 2x plus 1 on the top. So those are the kinds of things that we're going to seek to be solving using the method of substitution, use substitution. That is to say, we're going to try to undo the chain rule to recover this original function. And it can be tricky to identify when this is the case. But I think if you're really good at the chain rule, then hopefully you can look at some integrands and recognize this. There's also some trial and error in the doing of these types of problems. And I think that's perfectly okay. Like, it's not always obvious the right way to integrate a function when doing integration. And one thing that I think is really important is that you're just willing to try things and accept it when some things don't work out. Like, sometimes our methods of integration don't lead to the right thing, and that's okay. It just meant that we have to try something else. So let's talk through the method of integration, and then I'll leave a horde of example videos and videos on the finer points of substitution, like changing bounds of integration when doing definite integrals, and things like that for other videos. Okay, so I'm going to try to write down some general advice for how to do this, like step by step in this. And I feel like the first step when doing this is agree with yourself that you want to try substitution. So that might come from the hint of looking at the integrand for a piece that's the derivative of another piece. Okay. Like, so let's do one of the examples that I had up a little bit ago and examine that once again. So let's do the integral of sine to the 9th of x. That's sine x to the 9th, but we can eliminate a parenthetical by having the power be right there, times cosine of x dx. Okay, so I'm approaching this cold for the first time. Like, I haven't looked at this function before. I'm looking for, like, is it a basic function I just know how to integrate? No, it's not, because I've got tricky things here. I've got sine to the 9th, and I don't have an integral formula for sine to the 9th. Like, it's not a thing I have. So I'm looking at my integrand right here. This thing inside here is the integrand, the function I'm integrating. And I see, well, sine is the derivative of cosine with a minus sign, or cosine is the derivative of sine. And so I'm going to try one of those two things, and we're going to because there might be multiple relationships, so we're just going to try them. And step 2 is we're going to let u be equal to the complicated part. The piece in the complicated part. This thing right here, this sine, that's what I'm going to let be u. And then this thing right here is going to be the derivative of u. So what we're going to do is we're going to transform this by doing u, and it's going to turn into a simple function I know how to integrate. And then we'll unsubstitute, essentially. So this is going to be the thing that's the derivative of another piece, and then I will take and let that be u. Then I'm going to take the derivative of u, and so I'm going to have du dx is equal to, and now I didn't say what u is going to be equal to, so I probably should name that symbol in this piece right here. So we're going to let u be equal to, let's call it u of x. Okay, so this is going to be u prime of x. And then I want you to note that I have, so I'm going to do this thing with my differential in this particular case. And we do this a lot in the world of differential equations. So I'm going to move this differential to the other side. that means that du is equal to u prime times dx. This next step is going to have some subtlety to it, but that's going to be okay. So if I have u here equals to sine of x, then du dx is equal to cosine of x, and then du, and then I'm going to multiply by dx on both sides. So du is equal to cosine of x dx. Essentially, you can like kind of always shortcut that like multiply by, and you can just go du, take the derivative of this thing, and then put dx on the other side. Okay. The next step is we're going to find du in the integrand. And this might require like doing some like introducing a scalar or something like that, like a scaling function, a constant, in order to be able to get the thing to appear. And we'll see that in some example videos coming up. So I see cosine of x dx, and I see cosine of x dx. So this part right here is du. And if this fails, because it can fail, because sometimes we try things and they don't work, then it might be to go back to step 1. So if we fail, we might go back to step 1, and that's okay. If the entire integrand is in u, then we get to go to step 5 and rewrite. So this thing right here is equal to the integral of u to the 9th du. Well, that's, I mean, I know how to deal with that. Like, that's just the power rule for integration, no problem. And so now I'm going to go ahead and integrate. So we're going to rewrite. This should be entirely in terms of u. And then lastly, what we're going to do is we're going to integrate. And we'll unsubstitute. So we're going to integrate. And we're going to get u to the 10th over 10 plus some constant c. But our original function was an x. We want to be an x. So now we'll go ahead and substitute what u is equal to, and we'll have sine of x to the 10 over 10 plus some constant c. And as an optional step, we could check our work by taking the derivative of this expression and seeing that I get my original integrand back. Let's give it a mental try. I'm not going to write it down. I'm going to take the derivative of this expression right here. The derivative of plus c is 0. No problem. The derivative of something to the 10 is 10 something to the 9, and then I have to chain it out. My 10s cancel. Cool. So then I'd have sine to the 9, but I have to chain out the derivative of sine, so I'd get cosine, which is exactly what I started with. So I feel like this is a pretty good process for doing integrals using the method of substitution. And it kind of all starts by like being willing to do it. Like at some level, you have to just like let u equal something. And nobody's going to tell you what to make u. Like you just have to choose it. And my advice is to let it be the thing that we take the derivative of that's inside the complicated part. You'll get a sense for what that means as you do lots of problems. So there's some other subtleties as far as this goes, like what if we were doing a definite integral? Do I have to unsubstitute at the end if I'm doing a definite integral? And other concepts like that. But I'm going to leave those for another video and call this one good and say thank you so much for your attention today. I really appreciate you. Good luck, and I'll catch you again next time.